For r equal to 0, the real and imaginary parts of complex uh, exponential or sinusoidal. Imaginary, real and imaginary parts of a complex exponential or sinusoidal. Okay. For r is greater than 0, they correspond to sinusoidal signal multiplied by growing exponentials. That one is growing exponentials here. Growing here. And for r is less than 0, correspond the sinusoidal signals multiplied by, this is sinusoidal signals. Here growing. Okay. Multiplied with this growing exponentials. Growing exponentials. Growing exponentials. Here also. Upfront. Here when r is less than 0, corresponds sinusoidal signal multiplied by decaying exponentials. Here decaying exponential. So decaying here, decaying. These two cases are shown in figure 1.23. The dashed lines in the figure correspond to the function plus or minus c e power rt. The dashed lines. The dashed lines figure correspond to the functions. The dashed lines. Okay. Yeah, this is correspond to function plus or minus c e power rt from equation 1.42. 1.42. C mod c e power rt. That is here I will plus or minus mod c into e power rt. So we see that mod c e power rt is the magnitude of the complex exponential. Complex exponentials. Magnitude of the complex exponential. This is equation 1.42. C say mod c e power rt e power j into of omega naught t plus theta. Thus, the dashed lines, dashed curves act as envelope for the accelerated curve. In the figure, peak oscillations just reach the curves, and in this way, the envelope provides the convenient way visualize general trend amplitude of the oscillations. So, growing sinusoidal signal x of t equal to ce power rt cos omega of omega t plus theta. Here cos, this is cos signal. Say cos angular frequency omega naught theta t, this t here, and then this period, that's why theta. Here r is when r is greater than 0, when r is less than 0, then these are okay. When these r is less than 0, then cos omega c that is decaying sinusoid here. So sinusoid here. So x of t equal to c e power r t cos of omega t plus theta. That is e less than 0. So less than 0 means okay, cos omega angular frequency plus t and then theta angle that period that r equal due to this r is less than 0, this is happening, decaying signal happening. Sinusoidal signal multiplied by decaying exponential are commonly referred to as damped sinusoids. Yeah, sinusoidal signals multiplied by decaying exponentials. This is the decaying exponentials. Decaying exponentials. Decaying exponentials are commonly referred to as damped sinusoids. This is damped sinusoids. Example: damped sinusoids arise in response to RLC circuits and in mechanical systems containing both damping and restoring forces, such as automotive suspension systems. These kind of systems have mechanisms that dissipate energy. Here it is the important point. Dissipate the energy. The resistor dissipating energy, damping force dissipating energy, such as fraction. Resistor already dissipating energy. Damping force such as fraction, due to fraction, damping brake also, damping that reduction the energy. Fraction only happening the brake also. With oscillations that decay in time. With the oscillations like that, energy also reduced. Damping force reduced. There. Decay in example. Decay in time. Decay in time. Okay. Decay in time. Examples illustrating such systems and their damped sinusoidal natural response can be found in problems 2.61 and 62. Okay, that examples here we'll see there. Okay, and discrete time complex exponentials and sinusoidal signals. Discrete time complex exponentials and sinusoidal signals. First periodic continuous. Now we see here discrete time. Okay, as a continuous time, an important signal in discrete time is the complex exponential signal or sequence defined by same like a continuous time. Importance in discrete time, complex exponential or sequence like this: x of n equal to c alpha power n, where c and alpha c and alpha are in general complex numbers. This could alternatively be expressed in the form x of n, okay, x of n equal to c power beta n. So where alpha equal to here alpha, this alpha equal to what? P e power p. Okay, e power beta. The discrete time complex exponential sequence given in equation. Discrete time discrete time complex exponential given equation in 1.4 is more analogous to form the continuous time exponential. It is often more convenient to express the discrete time complex exponential in the form equation 1.44. Okay, x of n equal to c alpha power n. So x of n equal to c alpha power n equal to alpha equal to e power beta. So n already is there. So e power beta coming by that is alpha. Okay. Real exponential signals. Real exponential signals. If c and alpha are real, if c and alpha, c c and alpha, c and alpha are VL, we can have one of several types of behavior. One of several types of behavior. I illustrated figure in 1.24. 1.24. The real exponential signal x of n equal to C alpha power n. Generally, the condition when alpha is greater than 1, when alpha is greater than 1, like this. When alpha b 0 is less than alpha, and then less than 1, less alpha is greater than 0, less than 1, in between 0 to 1. In this condition, b, yeah, and c alpha is greater than minus 1, less than 0, it means minus 1 to 0, minus 1 to 0, c, minus 1 to 0, minus 1 to 0. Okay. And fourth condition, alpha is less than minus 1, less than minus 1. D. So if if C and alpha are real, we can have one of several types of behavior as illustrated figure 1.24. If alpha is greater than 1, sorry, mod alpha is greater than 1, the magnitude of the signal grows exponentially with n. Here the condition is that here alpha is greater than 1, alpha is greater than 1, that the magnitude of the signal grows exponentially. The magnitude of the signal grows exponentially. It's growing exponentially. Okay, growing exponentially. Signal grows exponentially with the n. With n, this is. While if mod alpha is less than 1, we have decaying exponentials. Less than 1. It means decaying, decay. Greater than 1 here, less than 1 here. Alpha is greater than 1 here, signal growing. Here less than 1, alpha is less than 1, decaying the signal. Then furthermore, if alpha is positive, all the values of C alpha power n are of same sign. If alpha is positive, all the values of C alpha power n are of same sign. But if alpha is negative, then the sign of x of n alternates. Note also that if alpha equal to 1, then x of n is constant. If alpha is 1, x of n is constant. Whereas if alpha is minus 1, x of n alternates in value between plus c and minus c. Real valued discrete time exponentials are often used to describe population growth as a function of generation, total return of investment as a function a day, month or quarter. This is example. All happening in plus C2 and minus C. So real valued discrete time exponentials are often used to describe population growth as function of generation and total return of investment as a function of day, month or quarter. Okay. Sinusoidal signals. Another important complex exponential is obtained by using form equation 1.45. 1.45. Okay. Yeah, and by constraining beta to be purely imaginary, so that alpha is mod alpha is greater than 1, sorry, equal to 1. Mod alpha is equal to 1. Specifically consider x of n equal to e power j omega not n. As in the continuous time case, this signal is closely related to the sinusoidal signal x of n equal to a cos of omega not n plus pi.